Okay, hi TIC VC Part 1. The first part of this screencast is to just introduce you to another notation for the derivative. So follow me here. And this early part, boys and girls, why don't you listen first, and then, because you certainly don't have to write down all of this. I just wrote down more than I needed to. But this first part here where I'm introducing you to a new notation, you don't need to write down all of this, unless of course you want to. Okay, so we've been using the Newtonian notations. So there are two, Leibniz and Newton kind of both discovered the calculus independently, or so they claimed. I mean, that's kind of a point of historical contention as to who discovered it first. And what happens is they both use different notations. And today, we as mathematicians and students use them both. So Newton used f of x as described in the function f prime of x as the derivative function. Leibniz used, f of x, which we know refers to y, the dependent variable. Dy dx, or dy over dx, is used by Leibniz in the form of, to refer to the derivative function. And when you write dy over dx, the way you say this is, you just say dy dx, okay? Everyone knows dy dx is the same thing as f prime of x, all right? So in other words, there are two ways to refer to the derivative function. One is f prime of x, or dy dx. And again, you say this as dy dx. So, and this is, again, Newton, this is Leibniz. Our text uses both. We will use both almost equally and interchangeably. I think all texts that I've seen use both almost interchangeably. Some other variations you will see, I've seen this version sometimes, y prime of x, and again, that means the same thing as dy dx, which means the same thing as f prime of x. So on one of your homework questions last week, number 9 on page 152, you were asked to find f prime of x if 2x equals 2x squared. And then you were told to evaluate f prime of x at x equals 1. Your answers, you found that, you used the limit of a difference quotient, and you found that f prime of x equaled 4x, and f prime of 1 equals 4, okay? Let's make this statement using Leibniz. Using Leibniz notation, you found that dy dx equals 4x, and then look at this. Dy dx at x equals 1 equals 4. So this part of the notation right here, right, dy dx evaluated at x equals 1, is saying what this is saying right here. And this is how you say it. Dy dx at x equals 1 equals 4. All right? So just make note of that. And again, I'm very picky about the notation because it's about the clarity in which you communicate, okay, in writing. All right. Along these lines of just different ways of saying the same thing, the results from above mean that the slope of the line tangent to f of x at x equals 1 is 4, all right? This phrase, slope of the line tangent to f of x at x equals 1, you will also hear that referred to as the slope of the function, or the slope of f of x at x equals 1, okay? Oh, here I wrote the slope of the function at x equals 1. You'll also hear and see the slope of the curve at x equals 1, all right? So all of these blue lines, when you say slope of the line tangent to f of x at x equals 1, that means the same thing as slope of the function, slope of f of x, or slope of the curve. All are synonymous, okay? So for this part of the screencast, take down what you need to. Let me just talk a little bit about Leibniz notation, just so it's not just kind of dumped on you. I want you to make a really important connection here. You know that the slope of a line from back in the day was just delta y over delta x, right? Or rise over run, or change in y, change in x. It turns out, boys and girls, that dy actually means rise of the tangent line. So dy here, the notation actually means the specific change in y that refers to the rise of the line tangent to a function. And dx means the run of the tangent line, right? So now that you know what these dy and dx means, it should make sense to you then, so it makes sense that dy dx then would refer to the slope of the line tangent, okay? One other thing that I could tell you too is, this will come up later on, but when we talk about differentials, right, dy and dx are called differentials. okay? They're called differentials. And I just told you what those differentials stand for. They're called differentials. The other important characteristic of differentials, okay? Yes, here dy is the rise of the tangent line, dx is the run of the tangent line, but differentials are also, they also refer to really, really, really small changes in x or y, okay? And you might wonder, why did I make a big deal about calling this really, really, really? Well, because I'm trying to underscore that we're looking at very, 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 very small rises and very, very small runs, okay? But the other thing is the question that you're going to deal with about a year from now is, okay, who decides what is small enough, right? When you say something is really, really, really small, it's an incredibly subjective statement, okay? Subjective means it's in the eye of the beholder. What I may regard as really, really small, you may not regard as really, really small. So mathematically, who decides when really, really small is small enough? And that's a question you'll talk about next year a great deal. But Leibniz notation uses a quotient of differentials, okay? The differential dy over the differential dx. All right? All right, so that part of the screencast, I don't think you actually had to write down a whole lot, but I just wanted to make sure you understood that notation. And now, come say hello. So this is BC Calculus. Say hi.
Hi, everyone.
Hello,
This is
everybody.
Oliver and Spencer and Severin, and they're here to pick up their Valentine. So hold on a second.